All right, guys, welcome to Quarantined Math Analysis. So, what we are going to talk about today is those 6 problems that I posted yesterday on the Google Classroom. If you haven't seen those, check those out, because what you want to do on those is find the derivatives of each. Now, I didn't hear from any of you guys over the past day about that, having any trouble finding the derivatives, so I'm going to presume that all went good on actually finding the derivatives of each of those. With that presumed, we're going to move on to finding the points that do not change, or the points with a zero slope in of the derivatives. So here's how we are going to do this, or of the function, sorry. Here's how we're going to do this. First, of course, we had to find the derivatives of each one. What we are going to do in this video is we are going to do number 1 and number 3. The others are going to be for you guys to try out independently. So first off, the derivative of number 1 here is 2x plus 3. And then the derivative of number 3 is 9x squared minus 8x plus 9. All right, so knowing the derivative of each of these is going to help us find the x value, or the coordinate, that has a non-changing slope. Now, we talked about how to do this with graphing the other day. Plug the function into Desmos or a calculator or whatever, see where it changes direction, where it kind of hits a peak or a low point, whatever it may be. But we can also do this mathematically. Now, I want you to think about it. If the derivative is what we use to find the slope, and we're looking for points with a slope of 0, how could we set up an equation like this? That's absolutely right. We could make the equations equal 0, right? Like if we took 2x plus 3 and set it equal to 0 and solve for x, then the x value we find should end up being the x value that is a non-changing point. So, this is pretty simple math at this point, right? Minus 3, and then 2x equals negative 3, divide by 2, and we get x is negative 3 seconds, or negative 1/2. So if we were to graph this function, which if you're at a computer and you can graph this on Desmos right now, by all means, do it. See if negative 1/2 for the x value, meaning negative 1/2 along the x-axis, is a point where that function changes direction, because it should be, according to our math. That's all we have to do on these simple problems like this. When you have a derivative that is just a binomial, just an x and a constant, all we got to do is set it equal to 0, solve, done. That is a non-changing point. Now, it's a little bit more complex whenever we look at a question like number 3. Because instead of just having a binomial, just an equation that takes us 5 seconds to solve, we have a polynomial. And if we set this up equal to 0, then it's a little bit more tough. We can't just subtract away the constant and divide and be done. We have an x squared in there, we have an x, all that kind of stuff. So we got to be creative. What do we know, being experienced mathematicians that we are, what do we know that would take a polynomial that's set equal to 0 and find x values for it? You got it. The quadratic formula. I bet you didn't think that was coming back this class, but here it is. The quadratic formula. If you don't recall the quadratic formula, then I will probably try to link a video explaining the quadratic formula into the Google Classroom so that you can check that out, you can review that, and you can kind of get yourself up to speed, because it has been a while. But if you do remember the quadratic formula, you know it goes like this. Negative b plus or minus the square root of b squared minus 4ac all over 2a. Of course, a, b, and c representing our 3 coefficients, 9, negative 8, and 9. A, B, and C. We're able to just plug them right into this quadratic formula, right? Well, negative b, that would be negative 8, So negative of a negative makes a positive. Plus or minus the square root, b squared, so negative 8 squared, minus 4 times a, 9, times c, 9, over 2 times a, or 2 times 9. Well, we can solve this bit by bit. So 8 plus or minus is not going to change, but here we have negative 8 squared. Okay, well, negative 8 squared is 64. Actually, heck, I mean, I can type this into a calculator, right? Like, why make life harder than it has to be? 8 squared is 64. Do keep in mind that if you put negative 8 squared instead of 64, or a negative number squared instead of just what it is, you need to have the negative and the number in parentheses and the exponent on the outside. I just prefer writing it in, doing the squaring in my head and typing that in. But that's just me. Minus 4 times 9 times 9. And we get negative 260. Oh, goodness. Oh, no, that's not a pretty number. You guys remember what happens when we have negatives under square roots? Not good things. They may have something to do with the letter I, right? Over 18. I don't know why that took me so much thought. So here's what occurs. We get 8 plus or minus the square root of negative 260 over 18. And yikes, square root of negative 260 is not a pretty number. All right, apologies for the cut there. I went on explaining some stuff, and then I kind of changed my mind about how I wanted to talk about this and to discuss this topic. Where I cut, we had found this, 8 plus or minus the square root of negative 260 over 18. Now, I want us to think about what square root of negative 260 means. Can we take the square root of a negative number? No. That's why a square root of a negative makes us bring in i's, or imaginary numbers. Otherwise, it's not real. Now, usually, we would go through the whole process of solving, simplifying this, figuring out what it is, even with that I in it, all that kind of stuff. But the fact of the matter is, our goal is to find the points where this line is not changing. Now, if our only solutions to this, our only ways to make this equation equal 0, the only ways to get this thing to have a point where the slope isn't 0 is to bring in an imaginary number, that means those points don't exist. There aren't any points that have a slope of 0. There aren't any points that are not changing. So once you start the quadratic formula and you notice a negative under the square root that we can't get rid of, then that means there are no coordinates where this particular line, this particular function, has a slope of 0. If you were to graph it, you would see something like we saw on the video the other day, where the line never changed direction. The entire time, it may have wavered back and forth a little bit, but it never changed direction. It never went from going up to down or vice versa. So again, like I said, if you're solving this quadratic formula and you get to a point where you have a negative under the square root and it would involve bringing in imaginary numbers, then your answer at that point of the problem is just, there are no coordinates where this line does not change. Because of a little confusion here on that one, and I feel like I didn't explain it super well, and I wasn't sure where I was going with it initially, or I changed direction with it. We're going to do number 4 as well. So I'm going to solve for the derivative of this. The derivative here is going to be 36x squared plus 8x plus 3. So this is a polynomial. For us to find the points where it does not change, we are going to set it equal to 0, and that allows us to do the quadratic formula on it. I'm going to rewrite the quadratic formula over here, negative b plus or minus the square root of b squared minus 4ac all over 2a. And I'm going to plug in what we know, a, b, and c. So we have negative 8 plus or minus the square root of b squared. That would be 64 minus 4. I should have just wrote an 8 squared. I don't know why I didn't. 4 times a, 36, times c, 3, all over 2a, or 2 times 36. Let's go ahead and simplify what we can here. Negative 8 stays the same, so negative 8 plus or minus. Underneath the square root, we are going to get 64 minus 4 times 36 times 3. We get negative 368. And then in the denominator, we have 72. By seeing a negative under our square root, that tells us that there are no solutions to this problem. There are no coordinates where a point is not changing. There are no points with a slope of 0. So that our answer would be no coordinates. There are no points that are not changing. If you do the quadratic formula and you find that you can simplify that, or it's a positive square root, then you can simplify it. You could even simplify it into a decimal if you want. I don't really mind. You would take this number, add whatever that square root is, and divide it by this. And then you would have a second coordinate where you take this number, subtract that, and divide by this. You would end up with 2 different points that don't change. That's why we have the plus or minus here. I will upload a video onto the Google Classroom going over the quadratic formula because I think it's been a long time and several of you may want just a little bit of additional catching up to do with that, an additional review. But if you have any questions, let me know. What I would like you guys to try out is numbers 2, 5, and 6 of those problems. See if you can find the coordinates, if any, that are not changing amongst problems 2, 5, and 6. On Monday, we will go over the answers to those, and we'll see the actual answers to every one of them. And then after that, forewarning, you may have a couple problems to try out independently overall, like with all this that we won't review. But yeah, so we'll do that on Monday, though. Try these 3 out. We'll go over them on Monday. If you have any questions, let me know. Otherwise, I'll see you then.